My name is Dr. David Wall. I'm a research officer at Teagasc in Johnstown Castle in the Soils and Land Use department. I'm currently leader of the nutrient efficiency subgroup within Teagasc, where I'm looking at fertiliser use efficiency and its interaction with soil, environment and different crop types. Today I'm talking about a project which we've started to look at the efficiency of nitrogen fertilisers used in agriculture, and more specifically nitrogen fertiliser formulation and its effects on production, greenhouse gases, water quality, etc. Nitrogen is a critical part of any production system. It probably confers the biggest increase in production, and since the time of the Green Revolution in the 1950s, nitrogen has been at the cornerstone of agricultural production. However, there has been a few new developments in terms of nitrogen and the nitrogen fertiliser types or formulations, with a few very recent technologies being released in Ireland in the last year, in the last 6 months in fact. It's really the species of nitrogen or the different pools of nitrogen that we put on affect how they behave in terms of both the plant capturing that nitrogen, but also in terms of the fate of that nitrogen in the environment, whether it's lost through greenhouse gas emissions or it's lost through leaching through the soil. So to that effect, Teagasc has embarked on a project funded by the Department of Agriculture, where we're looking at calcium ammonium nitrate, or CAN, which is the mainstay of Irish agriculture, urea, which is a lesser part used in the early part of the year by a lot of farmers, and then a couple of new technologies which encompasses urea as the main nitrogen source, but with other inhibitors. BBTP, which is trade name is agritane, is one of those, so urea plus this agritane additive, and also another one which is urea plus DCD, which is a nitrification inhibitor. I should say that agritane is a urease inhibitor. In terms of those two products, nitrogen source as CAN or calcium ammonium nitrate or urea, there's advantages in terms of perceived advantages in some respect by farmers. They're used to CAN. They've had a long tradition of using CAN, and they're happy to rely on CAN. They know that it works in different variable weather conditions and that. However, urea to a lesser extent, due to availability in some parts, it's more available in the springtime of the year and there's less demand for it during the summer period. However, urea has the potential to be more efficient in some respects than CAN, and where it's a real winner is in terms of its nitrous oxide profile or its nitrous oxide emission from the CAN. However, there are some areas that there is some concern in terms of losses through volatilization or ammonia lost to the atmosphere, which can dramatically increase nitrogen losses with using urea. However, in the last year in Ireland, but these things have been on the market globally for a number of years, agritane, which is an additive which reduces volatilization losses, which are probably the main loss in terms of agronomy, because it's much larger. So it's been measured. 10% of the total amount could potentially be lost if weather conditions. So that's sizable in terms of the farmer and in terms of the agronomy. N2O loss, obviously, with current greenhouse gas emission targets, is very important from a national standpoint in terms of our national inventory, and agriculture being a large proportion of our national greenhouse gas emission. Therefore, I suppose reducing emissions from agriculture through the likes of nitrogen fertiliser is also important, whereas the amount may not mean a huge amount to a farmer. Typically less than 1% of the nitrogen would be lost through N2O. However, when you count back in the volatilization losses and the indirect emissions there, that can increase N2O emissions. So In the current project, we've 2 years done. We're looking at both grassland, nitrogen fertiliser interaction with grassland, and in terms of a spring barley crop. We're currently measuring across a range of soil types or systems. So we have, in terms of the grassland, we have a site at Johnstown Castle, on a moderately drained site, in Moore Park on a very freely drained site, and also with our partners in AFBI in Hillsborough on a very poorly drained site. So we're kind of covering a little bit of climate but also soil conditions. In terms of the arable sites or the tillage sites, we have a short-term tillage after grass on a moderately drained soil at Johnstown Castle, and also at the site of the Agricultural Catchments Programme in Ballycarney in County Wexford. We have a very long-term, very typical spring barley site. Results in terms of these, we've had 2 very dry years the last 2 years, so really does test urea in that condition. Farmers are more used to using urea when it's in the spring, when it's wetter. And that's kind of been promoted in terms of the fertiliser companies and that. We've tested urea right throughout the season. So we have these treatments, we have CAN side by side with urea, and then also these inhibitor technologies. We've tested for the last 2 years under very dry conditions that you would expect losses in terms of volatilization of urea to increase. But also at shoulders of the year in terms of N2O being associated with wetter parts of the year or nitrous oxide loss. And we will need to test this over another couple of years to get a range in climatic variability so that it'll be robust enough to promote the farmers. So I suppose to summarise in terms of the grass work, urea and urea plus the inhibitor technologies performed very well agronomically. In terms of nitrous oxide emissions, urea performed better than the traditional CAN, and I suppose the urea plus the inhibitor technologies worked quite well as well. DCD working probably trending to be slightly better than straight urea. In terms of the volatilization losses, which can contribute to indirect N2O emissions but represent a loss for the farmer, the losses from urea were higher than obviously than both CAN, but you'd expect that. But with the application of the inhibitor technologies, we were able to bring those losses down in line with a typical CAN type position. So it bodes well for urea as a substitute. Again, this is a work in progress, and we will need to test this over another couple of years to get a range in climatic variability so that it'll be robust enough to promote the farmers. In terms of the tillage sector, spring tillage, we're working in spring barley, typically less than a half a kilo in that range on the long-term tillage site. In terms of other aspects, in terms of the farmer's use and his knowledge of using nitrogen fertilisers, there are a number of key things before he goes down to the route of selecting the fertiliser or nitrogen source type. Number one, I suppose, to achieve a high efficiency of that nitrogen, he needs to be sure that his other nutrients, phosphorus, potassium and stuff, pH, are in line. So soil testing is a critical first step to maximising the potential of all nutrients. The other aspect there is knowledge of the soil and the drainage characteristics. I suppose drainage being a big impactor on how nitrogen might be lost, be it that wetter soil types, more nitrous oxide or more emissions upwards, and drier soil types, I suppose, promote drainage and promote leaching downwards. So that's the first aspect. The other thing is, I suppose, crop type of time of the year, and taking account of the forecast, the weather forecast, before you'd apply. Urea has an advantage over CAN in respect to a lot of these loss mechanisms of nitrogen. Urea is more tightly held, or the ammonium, or the first product of urea when urea breaks down, can be more tightly held in the soil. So once it's moved into the soil, it can be held there for longer and is less prone to leaching. Can being 50% nitrate, it's the nitrate pool that we're trying to regulate in respect to losses. There's once it's spread, I suppose, and moves into the soil, that nitrate pool is there immediately. So if you get unfavourable weather conditions, leaching losses or ponding, we'll say, of the water on the surface for in a wetter soil, there's going to be more losses both upwards through nitrous oxide and downwards through leaching. Results on the grassland would show that urea has held up quite well in terms of productivity. On the sites we've produced between 10 and 13 tonnes dry matter of grass, which is very respectable by any standards. A 5-cut harvest, and at each of those timings urea and can were broadly similar. So even through that summer period. So that bodes well in terms of positive, in terms of replacing or substituting can with urea. In terms of the inhibitor technologies, they also performed similar to the can, which is the control standard here. So by and large, all our fertiliser treatments performed well in terms of their agronomics or in terms of their production. If we move in then to losses, in terms of nitrous oxide loss, which is the greenhouse gas, can had a much larger loss in terms of nitrous oxide than urea, which was significantly lower. So that bodes well for urea. In terms of the inhibitor technologies, they were also low, similar to urea in terms of those losses. In terms of the other loss mechanism, volatilization, which is probably larger in terms of the agronomic loss, again, can wouldn't have any risk of or limited risk of volatilization because it's a nitrate and ammonium type product. The loss would be more associated with urea. Losses were high or with urea, somewhat higher with urea. However, when agrotane is applied with the urea, it brings it back down to the similar levels or negates that loss similar to can.